Good morning, students. So we have come to the end of this course, and this is the last segment that we are going to discuss today, which is on string matching. I am sure you have already come across this term in the programming and data structures course itself, but just to give you a brief idea, so the problem statement is that you have some running text, and then you want to find locations where a substring, typically called a pattern, matches with a segment of the text, right? So you have some running text like A, B, A, C, A, B, 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 C, A, something like this. And so this is the text string, and you want to find CAB. Okay. So this is one occurrence of CAB, and this, when it matches with your pattern, actually returns the point at which the match was found. Okay. And also sometimes it returns the boundary. Fine. So I guess immediately, as I have noted this problem, you can think of multiple different areas where this can be used. So and in fact, this is used in text processing, in bioinformatics, and many other places. So for instance, think of a very simple example of finding words in a text document. Okay, fine. So string matching is one of the options by which you can try to find words in a particular text document. And say your simple task is, given a text document, you want to find a particular word W and count the number of times it has occurred in the occurred in the text document. Okay, so this is typically also called the frequency of the word. So you find out the word and the frequency. In this way, you might want to find out the word and the frequency of all the words in the text document. Okay, and string matching is one of the ways in which you can achieve this. So I would suggest that once I have taught you this algorithm, try to do the exercise that I just now mentioned. Find a word and the number of its occurrences in a running text document, and do it for all words. So you have a word frequency table. Okay, so you are given, say, a text document. Your task is to find out or compute a word frequency table where each word should appear in the running text, and the frequency is the number of times the word has occurred in the text. Okay, so we will talk about two different algorithms. The first one that we will discuss today is called the Rabin-Karp algorithm. And the second one that we will discuss next day is called the Knuth-Morris Pratt algorithm, or more popularly known as the KMP algorithm. Okay, so uh, I have chosen this particular algorithm as the first one because this continues from your previous topic that I taught you on hash tables. Okay, you will see that how hash tables or hashing in general can be used to uh, achieve real world problem solving like string matching. Okay, so the idea is as follows. So you are given a text string and you are given a pattern to be found in the text string. Okay, so this is the task. These are your two inputs. Fine. So what you do is you calculate the hash value. So this is the mm, top level idea. Hash value for the pattern, right? And for each m character subsequence of the text string. So you have a hash for the pattern and you have a hash for each of the m character subsequence of the text string. Okay. Now there can be two things that can happen. If the hash value are unequal, okay, if the hash values are unequal, the algorithm will calculate the hash value of the next m character subsequence of the text string. If the hash values are equal, then the algorithm will compare the pattern with the m character subsequence subsequence character by character. Okay, so there are two parts in the algorithm. So first part is you compute a hash value for the pattern and you compute a hash value of m character subsequence, okay, of the string. And then if the two hash values are unequal, then you slide one character. So this is also sometimes called the sliding window. So you slide one character and you take the next 10 characters, compute their hash, okay, and compare it again with the hash value of the pattern, and you continue this. In case if the hash values are equal, then you know that there is a chance that the m character subsequence is going to match with the pattern, and in only such cases you make explicit character by character comparison. So as you understand, this hashing directly reduces the total number of computations that you need to do, that you would have needed to do, okay, if you had to do the whole thing character by character. So the character matching, remember this, is required only when the hash values match. Fine. So this is the only case when the character matching, explicit character matching is required. Now, if your hash function is very poor, then you will collide a lot and explicit comparisons will be more. However, if your hash function is good, then your collision will be very less and your explicit comparison will also therefore go down. So how do we achieve this? Okay, so let us first try to set up the mathematical aperture, okay, for this. So let us consider an m character sequence, okay, as an m digit number in, say, base b. Now b is the number of letters in the alphabet. Fine. Now the text subsequence say t I to t I plus m minus 1 is mapped to the number xi, where xi is expressed as ti into b to the power m minus 1 plus ti plus 1 into b to the power m minus 2 plus so on ti plus m minus 1 b to the power 0. Okay. So now from xi we can compute xi plus 1, okay, for the next subsequence. Now, in order to do this, we need to find a smart way, right? So every time we cannot do this computation, like for every I, we cannot afford to do this computation. So we will try to have a tricky manipulation of xi in order to obtain xi plus 1, okay? And as I'll show you, this can be done in constant time. So it is very apparent if you see the structure of xi plus 1. So xi plus 1 looks like this. T I plus 1 into b to the power minus 1, sorry, b to the power m minus 1 plus t I plus 2 into b to the power m minus 2 plus up until t I plus m into b to the power 0. Okay. So now if you look at these two expressions, xi and xi plus 1, it, it becomes immediately apparent that xi plus 1 can be obtained as xi into b, as if you are shifting left one digit, minus ti into b to the m, subtract leftmost digit, okay, plus t I plus m, add the rightmost new digit, right? So in this way we can slide over, and from the previous xi we can compute the next xi plus 1 in just constant time, okay? Now if m is very large, then these numbers xi plus 1 etc can be very, very large, okay? So in general bm is large. Could be very large. So therefore what we do is we always express these numbers as modulo q, okay, where q is a prime. Fine. So this is actually easily doable because of the following properties of the modulus function. Okay. So I guess all of you would remember from your +2 days that x mod q plus y mod q mod q is nothing but x plus y mod q. Okay. Similarly, x mod q mod q is nothing but x mod q. Okay, as simple as that. So for these two reasons, now we can transform xi to hi's, which are in the modulo domain, ti into b to the m minus 1 mod q plus ti plus 1 into b to the m minus 2 mod q plus so on and so forth ti plus m minus 1 mod q mod q. Okay. Similarly, h I plus 1 is h I into b mod q minus ti into b to the m mod q plus ti plus m mod q mod q. Okay. So based on the above two properties, this can be easily derived. Fine. So now given this, we can write the Rabin-Karp algorithm. Given this transformation, we can write the Rabin-Karp algorithm. So the algorithm is very simple once you have written this formulation properly. Let us say that n is equal to the length of the text string and m is the length of the pattern. Okay. Let us define h as b to the m minus 1 mod q. Let us say p is equal to 0 and t0 is equal to 0. Okay. Now for I equals 0 to m, we compute the first two things. P is equal to d into p plus pi mod q and t0 is equal to d into t0 plus ti mod q. So this is the hash of the pattern and this is the hash of the first the first m characters of the string t, right? Now for s equals 0 to n minus m, since we have already consumed the first m, so we run from 0 to n minus m. If p is equal to t0, if this is true, then if P1 to M is equal to T S plus 1 through S plus M we trigger pattern found at shift S. Okay, so this part actually you can interpret as an explicit character by character matching. Fine. If this is not true and if S is still less than n minus m, then what do? We set Ts plus 1 as d Ts minus Ts plus 1 into H plus T S plus M plus 1. Okay. So this is how you try to now. So this Ts plus 1 will in constant time compute the next hash from given the value of Ts, right? So the algorithm is as simple as this. Now let us take a small example and check out how it functions. Let's say we have a string like this. Let us say we have a string of this form. Okay. And let us say our q is 13 in this case. Okay. And we want to calculate the hash for the pattern 14152, right? So that is this one 14152. We want to calculate the hash for this, and as you see the numbers are between 0 to 9. So the alphabet here is 0 to 9, and therefore base is 10, okay, which is the number of elements in the alphabet. So given this, we can compute the hash for 14152. If I tell you that the hash of 31415 is given to be 7, it would be very easy for you to compute the hash of 14152. Okay. So let us see explicitly. So hash of 14152 is equal to 10 into 31415 minus 3 into 10 to the 4, okay, modulo 13 plus 2 modulo 13, that is 8. Okay. So as simple as that. Now you see that, as I said earlier also, there could be collisions. Okay. And you will see, like, if you keep on computing like this, then this series 67399 will again lead you to a hash value of 7. Okay. So this is something that you need to be careful. So the complexity of this algorithm is straightforward to calculate. So now you have seen that the variable s that runs, right, n minus m times. Okay, right? So it goes n minus m times, the first time being directly compared, and after that it runs n minus m times. Now in this loop, like, what could be the worst case? The worst case is where collision occurs in every step, in every slide. Okay. So as you slide the window, in every slide there is a collision. So this is the worst case. And for each collision, each such collision, you will have to do a exact character by character match. Right? So there are m characters. So you will have to match m characters of the text string with the m characters of the pattern. Okay. So this character by character match will take time order m. Okay. And since in the worst case there can be n minus m times such collisions taking place, so the cost would be n minus m into m, and therefore roughly the complexity of this algorithm would be n minus m into m. So that ends our discussion on the Rabin-Karp algorithm. And in the next lecture, we will start off with the North Port algorithm.